Okay, so I was saying that we'll be looking at acid-base balance. Okay, acid-base balance. And as we all know what an acid is. We know what a base is, and we know what pH is. Okay, and basically an acid is a proton donor. So proton is H plus. Okay, and the H plus ions determine the pH of the system. Okay, and because the human system is or the human system consists of a lot of proteins and enzymes, and we know that enzymes work at specific pH. Okay, so it's important for us to keep the pH range of the body within certain limited values. Okay, good. So the pH of the body is 7.35 to 7.45. So it's a range between 7.35 and then 7.45. So we must ensure that no matter what happens within your system, okay, no matter what you eat or what comes out from you, your pH must be within this range. Okay, but in some conditions, we will see that the pH can either exceed this range or go very low. Okay, so we'll be looking at certain acids and certain bases. Okay, we know the concept of conjugate base. So if you have an acid, we have its conjugate base. Okay, and if we remember from high school that if the acid is strong, then its conjugate base is a weak base. Okay, and vice versa. If I have a weak acid, then its conjugate base is going to be very strong. Okay, now when we take the human system, some of the acids that we are going to meet, we are going to meet HCl, and then we are going to meet um, this will be NH4 plus. Okay, and then certain amino acids too, and most importantly the phosphate acids. Okay, as well as this important acid, which is the bicarbonate acid. Okay, the bicarbonate acid is a very important one. So the ones that we should know are HCl, NH4 plus, then the phosphates, and then the bicarbonates. Okay, and we know how the bicarbonate is produced. When you have carbon dioxide plus water, you get bicarbonate. Okay, the enzyme for this reaction is the carbonic anhydrase enzyme. That combines carbon dioxide and water to get the bicarbonate acid. Okay, and this can also break down to form H plus and then HCO3 minus. Now remember that H2CO3 is a weak acid. Therefore, its conjugate base HCO3 minus is a very strong base. Okay, and we'll look at them. Now, in order for the body to maintain such limits of pH, okay, the body must have a specialized system called the buffer system. Okay, so as we remember from high school, a buffer system is a system that is able to maintain its pH, okay, irrespective of addition of either acids or base. Okay, so now you see, if I inject you with H plus ions, okay, your body has a way of dealing with it such that the pH does not change any significantly. Okay, so let's look at some of the buffer solutions. Okay, let's see. In fact, all these things are explaining the concept of acids and pH, which we already know. So I'm not going to spend time over there. Okay, good. So now let's come to this slide. Now, if we have pure water, okay, and I put in, we know pure water has a pH of 7, okay. If I add, let's say you have 1 liter of pure water. If I add 100 millimoles of HCl to this, okay, the pH of the pure water will change from 7 to 1. Okay, we know pH is equal to negative log of H plus ion. So here, if I have 100 millimoles, okay, in 1 liter, okay, the concentration is going to be, 100 millimole is 0.1 mole. So the concentration will be 0.1 molar HCl, and that pH is equal to 1. Okay, but if I take phosphate, okay, and I add 100 millimoles of HCl, you realize that the pH will only change from 7 to 6. Unlike this one, which pure water, which changes from 7 to 1, here is going to change from 7 to 6, because the phosphate can act as a buffer. Now, the principle that I want you to note is that it is the presence of the H plus ions that determine the pH. Okay, not necessarily the presence of the the acidic compound. Is the H plus ion. So if I add this HCl to this phosphate, okay, some of the H plus will combine with the phosphates, okay, and then there will only be left with few H plus ions. Okay, that's why the pH moves from 7 to 6, but not from 7 to 1 as we see over here. Now, when I take a person's plasma, your plasma has other buffer systems, okay? So even if I inject someone with 100 millimoles of HCl, you notice that the pH, we know the pH of buffer of the plasma is 7 points. The average is 7.4. If I add this 100 millimoles to it, you see, the pH will only change small to 7.0, because the buffer systems will absorb the H plus ions, okay, such that only little H plus ions will be left to cause that change of pH. Okay, good. We can even go a bit further. Okay. When we have blood, when you have whole blood, you notice that the pH just changes from 7.4 to 7.35. Okay. But if we take the whole organism, you notice that even when you inject the person with 100 millimoles of HCl, the pH changes from 7.40 to 7.39, because the more buffer systems you add, okay, the better the organism's ability to resist the change in pH. Okay, so that's a very important concept that you should note. Now, when we take the human being, there are a lot of buffer systems, okay? And as I said, the first buffer system that we look at is the bicarbonate buffer system. This is the bicarbonate buffer system. And we also talked about the phosphates buffer system, okay? And you have proteins. The proteins in the body can also act as a buffer system, as well as hemoglobin itself can also act as a buffer system. And then skeletal muscles can also act as buffer system. Even cells themselves can act as buffer system. So there are a lot of buffer systems in the body, okay? And they are all in equilibrium, okay? They are all in equilibrium. Good. Now, as I said, the first buffer system that we are going to talk about is the H2CO3, and the bicarbonate buffer system. Now, what's going to happen is that, as I said, we get bicarbonates from carbon dioxide and water. Okay, that will give us H2CO3. Now, when you get this H2CO3, it's going to dissociate into H plus and then HCO3 minus. Okay, good. So this system is the buffer system. So what's going to happen is that if let's say I inject someone with H plus ions, okay, what's going to happen is that this is the conjugate base. The conjugate base is going to react to the H plus ions that I injected to the person, and it's going to move the reaction to the right, okay, and that's going to give us more of H2CO3, and this H2CO3 will break down to water and then carbon dioxide. Then you breathe the carbon dioxide out. Okay, so this is how the bicarbonate buffer system works. So if I if I inject someone with H plus ions, okay, the bicarbonate ions, HCO3 minus, which is the conjugate base, okay, will react with the H plus ions and give us more of H2CO3. This H2CO3 will break down to carbon dioxide and water, and then you breathe the carbon dioxide out, okay? The water will remain in your system. So that's how the bicarbonate buffer system works. Good. So I'm not going to look at all this. I'll just emphasize this. I'll just emphasize this equation, which we all know, that pH is equal to pKa plus log of salt over acid. Log of salt over the acid. The salt here represents the conjugate base. Okay, the conjugate base. Or if you look at it from this side, the salt is the conjugate base, the acid is the H2CO3. Now, the reason why this equation is very important, okay, the Hasselbalch's equation. The reason why this equation is very important is because, okay, we know that for a buffer, okay, a buffer works best at a pH which is equal to its pKa. Okay, so that's another concept. A buffer works best when the pH of the system is equal to the pKa of the acid involved. Okay, so that means that for the pH to be equal to the pKa, then this whole part should be 0. So that pH is equal to pKa. That means that log of salt over acid should be 0. And the only way log of salt over acid can be 0 is when the salt concentration is equal to the acid concentration. So that they cancel out, then we'll be left with log 1, and log 1 is 0. So in this case, we get the pH being equal to pKa. Okay, later on, you will see the importance of what I've said. Good. So that is exactly what is being stated here. That when the conjugate base and then the acids are equal, when their concentrations are the same, you cancel out and you'll be left with log 1. Okay, and log 1 is 0. Then you get pH is equal to pKa. Okay, so how best the buffer works, okay, is determined by the ratio of the conjugate base and then the ratio of the H plus. If they are the same and the ratio is 1, then you get the pH to be equal to pKa. Okay, at that pH, the buffer is going to work very well. Okay. Now, let me add this concept. Okay. If the ratio of the conjugate base and then the ratio of the acid, okay, is, let's say, 50:1 or 1:50. Okay, if it exceeds this ratio, that system cannot work as a buffer. Okay, at that pH, it can't work as a buffer. So the range for a buffer to work is between the range of log of, that's, this side becomes log of 50 over 1, okay, or log of 1 over 50. That's the range at which the pH works. Now, when you find 50 over log of 50 over 1, you get 1.7. So what I'm trying to say is that if you want to maintain, if let me give you an example. If I want to maintain the human blood, okay, at a pH of 7.4, that means that the substance that I'm going to use as a buffer, okay, should have a pKa also of 7.4, because, and that would be the best buffer. So the best buffer is the buffer in which the pH is equal to the pKa. So for the human system, if I'm able to get a certain acid, okay, whose pKa is equal to 7.4, then that substance can serve as a buffer in the human system. But it's difficult to get such substances, okay? So then we give it a range. Okay, so if I can get any substance such that when I add 1.7 to it, I can get 7.4, that substance can fit. Okay, or when I subtract 1.7 for 1.7 to it, I can still get the pH of the system. That substance too can still work perfectly as the buffer. Okay, so let me give you an example. So when you take the bicarbonate system, you see the pKa, the acid over there is the carbon dioxide acid, okay? Carbon dioxide is an acid. The pKa is 6.1. Now the pH of your system is 7.4. Okay. So if I have 6.1 over here, then I know that I have to add 1.3 to it to get 7.4. Okay, and then 1.3 is within 1.7. So that means that the bicarbonate system can function as a good buffer. Okay, so this session is ending. Okay, so we will continue. I'll repeat this point when we come back. Okay, and if you have your questions, note them. When we come back again, you can ask them. Okay.